Hi students, welcome to the channel NCERT Maths Tutor. If you like this video, please click the like button, share and subscribe. In this video, I'm explaining the concept principle of mathematical induction. Here we use a mathematical statement. So consider a mathematical statement 1 plus 2 plus 3 plus so on up to plus n is equal to n into n plus 1 divided by 2. This is a mathematical statement which is already proved for a set of n natural numbers. Here n represents the set of n natural numbers. So now, if you want to verify whether this mathematical statement is a true statement or a false statement, then the one method you can use is that if you check this particular mathematical statement for all the values of n is a set of natural numbers, and if you begin with n is equal to 1, n is equal to 2, n is equal to 3, and if you reach to the end, and for all the values of n, if you get the answer true, then we can say that it is a true statement. For example, see, I have taken n is equal to 1. So, I will consider here for n is equal to 1, from the left hand side, the first term, that is 1, and from the right hand side, this entire term. If I put the value of n over here, so I get here 2 by 2, that is equal to 1. And on the left hand side, the first term is equal to 1. So, here left hand side is equal to right hand side. So, for n is equal to 1, this statement is true. Then next I am checking for n is equal to 2. Again for n is equal to 2, right hand side we get the value 3. And here on the left hand side, we have to take first two terms. So, 1 plus 2, that is also 3 only. Then for n is equal to 3, I get the value 6. If I put the value of n in this, then I get the value 6, and here from the left hand side we have to take 3 terms, 1 plus 2 plus 3, that is also is equal to 6. See, like this way we can prove this particular statement for n natural numbers, but the set of natural number is a huge collection of values. So, if you do this process, then it is a never-ending process. So, you can't stop this process. It will continue as it is for n is equal to 1, 2, 3, 4, 5, 6. So, that's why by using this method, it is very difficult to, it is impossible to prove the particular statement or to check the particular statement whether it's a true statement or false statement. So that's why only in a short method we can check whether the statement is a true statement or false statement, and that method is known as the principle of mathematical induction. So here in the case of principle of mathematical induction, instead of checking the statement for many values, we check the statement for some specific values. That means in the first step, we check the statement for n is equal to 1. And if it is true for n is equal to 1, then only we proceed to the second step. And then in the second step, we make the assumption that the given statement is true for some positive integer k. And in the third step, by using the assumption of n is equal to k, we try to prove that the statement is also true for n is equal to k plus 1. So, if you get that, then we can say that the entire mathematical statement is true for all the values of n. So, these 3 steps we follow in the case of principle of mathematical induction. So, instead of checking a given mathematical statement for many values of natural numbers, we check here only for n is equal to 1. Then in the second step, we make the assumption for n is equal to k. And then in the third step, by using the assumption, we try to prove that the given statement is true for n is equal to k plus 1. So this method we are applying here. So now let us understand this method clearly by applying the method to this example. See, I have taken a mathematical statement which will give you the set of or sum of n natural numbers. I have here 1 plus 2 plus 3 plus so on up to plus n is equal to n into n plus 1 divided by 2. See, So the statement is here P of n or Pn. So Pn is equal to the given statement. Now, the first step we have to follow, the first step of principle of mathematical induction is that we have to check the given statement for n is equal to 1. So, for n is equal to 1, this becomes P of 1. Now, here we have to take the terms from the left hand side as well as right hand side. See, left hand side for n is equal to 1 means it is the first term. So you have to take the first term from the left hand side. So on the left hand side we have the first term as 1. So that is equal to 1. Then on the right hand side we have to take this entire term, that is n into n plus 1 divided by 2. But here n is equal to 1. So wherever you have n, there you need to put the value of n. So 1 into 1 plus 1 divided by 2. So 1 is equal to, this becomes 2 by 2. So 1 is equal to 1. So here LHS is equal to RHS. That means here now we can say that the given statement is true for n is equal to 1. P of 1 is true. This is the first step we have to do. And this step is also known as the basis step. Next, the second step is, now here we have to make the assumption. We have to assume that for some positive integer k, the given statement is true. So wherever you have n, there you have to replace the value k. So after making the assumption, we get a new statement, that is P of k or pk, 1 plus 2 plus 3 plus k is equal to k into k plus 1 divided by 2. Let us take this one as statement 1. See here how you got this one. Wherever you have n, replace that n with k. This is the assumption we have made. Next step is that in the third step, we have to prove that now the given statement is also true for P of k plus 1. So, you write the statement in the form of P of k plus 1. P of k plus 1 means it is the next term, the term after k. So, if you write this particular mathematical statement in k plus 1 form, then it becomes 1 plus 2 plus 3 plus so on up to k. Then after k, we have the next term. The next term is k plus 1, right? If you have 1, the next term is 2. If you have 2, the next term is 3. So here after k, we get k plus 1 term. So write that. 1 plus 2 plus 3 plus so on up to plus k plus 1 is equal to, on the right hand side, we are talking about now up to k plus 1. Here this is up to k. Now here the last term is k plus 1. So here wherever you have k, that becomes k plus 1 now. So this become k plus 1 and this k become k plus 1. And here we have that plus 1 divided by 2. Then this is the statement which we have to prove now. So how to prove this? See, to prove this, what we do is here, we take the left hand side of P of k plus 1. That is this one, this part we take, and then if we reach to the right hand side, that means it is a true statement. So now let us take the left hand side. We have on the left hand side 1 plus 2 plus 3 plus so on up to plus k of k plus 1. See now here on the left hand side, if you just take this much part and if you compare this part with our assumption, see, this is nothing but this k into k plus 1 divided by 2, right? We have already assumed 1 plus 2 plus 3 plus so on up to plus k is equal to this one. So now you just replace in this place this value k into k plus 1 divided by 2 plus this one k plus 1. Now here you can take the common denominator 2. So if I take the common denominator as 2, this 2 you can multiply with this. So k into k plus 1 plus 2 into k plus 1 divided by 2. Now here we have two terms. So among these two terms, the common term is k plus 1. Here also we have and here also you have. So we can take that out. So if I take here k plus 1 out, in this case the remaining term is k. Then here the remaining term is 2. So we get here k plus 1 into k plus 2 divided by 2. But we need the final result in the form of k plus 1. That is here. We have to reach to this solution. So already here we have k plus 1. But in this place we have k plus 2. But here we have to get k plus 1 plus 1. So the one thing you can do is this you can split and write. See, k plus 2 is nothing but k plus 1 plus 1, right? That is equal to k plus 2 only. K plus 1 plus 1, so that is k plus 2. So I'm writing this one in the form of k plus 1. K plus 1 plus 1 divided by 2, and this is nothing but see our RHS. So we have reached to the RHS side. That means now we have proved that the statement is also true for P of k plus 1 by using the assumption of P of k. So, hence, by using the principle of mathematical induction, now we can say that the given statement is true for all the values of n, all the set of natural numbers. So, this is the method which you have to follow in principle of mathematical induction. If you like this video, please subscribe to the channel NCERT Maths Tutor to get more regular updates. Thanks for watching.